So in this lecture video, we're going to talk about transforming a state of stress from the x, y, z coordinate system to the x prime, y prime, z prime coordinate system. Okay, so we have a original coordinate system we want to transfer to a known coordinate system, x prime, y prime, and z prime. All right, so in order to do this we can start off with a 2D example just to make it nice and simple. So we want to go from the x, y coordinate system to the x prime, y prime coordinate system. So to do this, we can use our transformation matrix, right, where we have x prime, y prime is going to be equal to our transformation matrix, cosine theta, sine theta, minus sine theta, and cosine theta times our original coordinates x and y. Okay? So what that looks like is if we have a vector going along the x-axis, right, and we draw a two vectors going along it, we would have, and we know that the angle between the x-axis and the x-prime axis is an angle theta, right? We know that the projection of the vector along the x-axis would be equal to cosine, or the adjacent side of this right triangle, theta. All right? So that's where we have our cosine theta here. All right? All right. In a similar sense, the projection due to the y-axis um, would be equal to if we had a vector going along the y-axis, right, and we drew a right triangle here, right, this angle here is equal to 90 minus theta. Therefore, this angle would be equal to theta here. So the vector that goes along the y on the x prime axis would be equal to sine of theta times the vector going along the y direction. Okay, so that's where our sine of theta comes in. Now, the sine of theta, again, remember, is equal to the cosine of 90 minus theta. All right, so we can rewrite this transformation matrix, that's in terms of cosines and sines, in terms of all cosines. Okay, so this matrix, our transformation matrix, has been transformed from sines and cosines to just cosines. So this matrix is going to be called, or the terms within this matrix are going to be called our directional cosines, and they're going to be denoted with the terms x prime. They're going to be denoted as x prime um, with the letter n. So n in this case, what it stands for is cosine. Okay, and then there's going to be two additional indices, where the first index represents the new coordinate system. All right, and then the second coordinate represents the second index represents the old, or the original coordinate system. All right, so using this, and this is something that you did in statics. You had to develop like unit vectors with directional cosines, where you had like the unit vector along the x-axis was equal to cosine of some angle alpha, and the unit vector along the y-axis was equal to some cosine of some angle beta, and u of z is equal to cosine of some angle gamma. All right. So like you've done this in the past. This is just a new way, a new orientation of a way of writing it. So the cool thing about this is that you can use it in 3 dimensions to transform systems from x, y, z uh, to x, y prime, x prime, y prime, and z prime coordinate system. So if we define, so in order to do this, to kind of show this graphically what you can do, so we're going to define our new a new unit vector nx prime that goes along the x prime axis here. Okay, and then it will have that unit vector can have, you can think of it as having three projections or three components along the old x, y, and z coordinate system. So we have the component that goes along the x-axis here, um, which we can call nx prime x. All right, we have the component that goes along the y-axis, nx prime y, and we have the component that goes along the z-axis, nx prime z. Okay, so we can write them either in either of these two uh, forms for a vector. All right, and then the thing that should be a little bit obvious, but just want to confirm, is that x prime is the nx prime, or the unit vector that goes along the x-axis, x prime axis, is perpendicular to the y prime axis and the z prime axis, and then the y prime axis and the z prime axis are also perpendicular to one another. Okay, so so using this, all right, um, we can define, we can take using these directional cosines, we'll be able to develop a way to transform any state of stress. So in this case, our state of stress in 3 dimensions is equal to our 3 normal stresses, sigma x, sigma y, and sigma z, as well as tau xy, tau zx. All right, and tau yz. All right, so we can transform it to another coordinate system where to the x prime, y prime, and z prime coordinate system using these directional cosines. Okay, so really quickly, I just want to show you that this is what it would look like in 3 dimensions. Is that n x prime x would be equal to cosine theta x, where theta x would go from the x-axis to our new x prime axis. Theta theta y would go from our original y-axis to our new x prime axis, and then theta z would go from our original z-axis to the x prime axis. Okay, so using those directional cosines, we can come up with this is again what this picture is of a stress element that's been cut at an arbitrary angle relative to the original xy prime coordinate system, where the angle is perpendicular, or the angle, or the vector x prime is perpendicular to that new face that's been cut. So we can say that a of x, we can develop equations for a of x, a of y, and a of z, which are the faces along the x, y, and z axes. And then what we can do, just like we did in 2 dimensions, is that we can solve for we can sum all the forces along the x prime direction and set them equal to 0. And then we can then use that to solve for sigma x prime. And then following a similar process, we could determine a set of algebraic equations for all the different stress components, which is shown in this set of algebraic equations. So we could solve for the new state of stress, x prime, y prime, z prime, using these equations where we have our 3 new normal stresses and our 3 new shear stresses. Okay, so the last thing here is You can also solve this same equation, or you can solve for all the terms simultaneously if you want, using the transformation, using the matrix equation, which kind of combines all these equations into uh, one single method. So the only thing is you use it's the same formula as we had in 2D, where we had our transformation matrix times the original matrix, original stress matrix times the transformation matrix transposed. So just the only thing that's different now is our transformation matrix, instead of being a 2 by 2 matrix, is a 3 by 3 matrix, and is filled with all of our directional cosines. All right. So that concludes this problem, this lecture on this video on how to transform a state of stress from our XYZ coordinate system to the x prime, y prime, z prime coordinate system using directional cosines.